This is a fifth video related to sections 5.1 and 5.2 on linearization and nullclines and trying to analyze, in general, nonlinear systems. And I'd like to try to do this one quickly, make it shorter than the others, but what I want to do is I want to, instead of just focusing on doing things by hand, I'd like to combine the computer and Mathematica specifically with doing things by hand. So here's the system that we're going to consider, and it's actually a pretty complicated system. Focus up on the screen there. dx dt is going to equal x times negative 4x minus y plus 160. And dy dt is going to equal y times negative x squared minus y squared plus 2500. Okay, I'm actually taking this directly from the book. It's system from exercise 10 in section 5.2, and that's really the same system as exercise 12 in section 5.1. All right, so we want to try to make the phase plane with this. And let's, right off the bat, go ahead and use Mathematica to help us along the way. And while you certainly want to be able to do things like this by hand for the exam, to save some time with homework, you don't have to do every problem by hand completely for the homework. You can use Mathematica or perhaps HPG System Solver to help you refine what you're doing. Good place to start with a system like this. Is that showing up bright enough? It's as bright as it goes.
Yeah.
Okay. Good place to start with something like this is to define functions representing the right-hand sides. So again, the dx dt was x times the quantity negative 4x minus y plus 160. I'm going to call that little f of x comma y. That will be the first component of the vector field. G of xy is y times the quantity negative x squared minus y squared plus 2500. All right, so those functions are entered. Now again, you certainly should be able to do it by hand, but as long as we've got Mathematica up, I'll go ahead and find the equilibria with Mathematica. So I'll solve this system of equations. Set the right-hand sides equal to 0 and solve for x and y. All right, can you see that? We get a bunch of answers. Look at that. The origin, 0, 0. X is 30, y is 40. X is 40, y is 0. X is 770 over 17, y is negative 360 over 17. X is 0, y is negative 50, and x is 0, y is positive 50. Lots of equilibrium points. Well, if this were a competing species model, which maybe, or some kind of species model, interacting species model, maybe we'd want to only focus on the first quadrant, so we'd ignore the ones with negative x or y values. Let's at least initially assume that. Well, I don't know if we'll have time to perhaps consider the ones with negative x or y values, but at the moment, let's not worry about it. Let's do something that confirms these answers visually. What I'm going to do is I'm going to use ContourPlot to plot the nullclines. The x nullcline is where f of xy is 0. If you zoom in on that, I've made it a little smaller here. The y nullcline is where g of xy is 0. ContourPlot will plot those equations. And looking at the equilibrium points Certainly I want to let x and y perhaps go up to in the ballpark of at least 50 or so. And if I did want to include the negative points here, I want to go to at least say negative 20 there, and let's see, well, negative 50. Why don't I go negative 75 to 100 for x and negative 75 to 100 for y. Although again, I think mostly we're going to focus on the first quadrant here. And to make it easier to see, I better do contour style thick, and I want to make different colors, so I'll do a red for the x nullcline and a blue for the y nullcline. Not plot style. When you use ContourPlot, you've got to use contour style. So here we go. There's the graph of the nullclines. Now remember, the x nullcline was in red. That's where dx dt is 0. And the y nullcline is in blue. That's where dy dt is 0. Just double checking to make sure I've got everything in there right. Looks pretty good. Where red and blue cross, that's where we got equilibrium points, where dx dt and dy dt are both 0. So you can see, for example, right there, red and blue cross, that's the point 0, 50, which was one of the equilibria. Here's one with the negative, 0, negative 50. That's the second equilibrium point. This one right there is when looks like x is about 40 and y is 0. And going back up here, higher, that was an equilibrium point. X is 40, y is 0 is right there. This one with this finger right down here, that's x equals 30, y equals 40. And then going back up here, that is one of the ones that we got. X equals 30 and y equals 40. That brings us to 1, 2, I forgot the origin. The origin is 1 also. 1, 2, 3, 4, 5 equilibria. The sixth one is this one over here that's got a negative y value and a positive x value. But again, let's just focus on the first quadrant. So these are your nullclines. I can go ahead and use, now my thought process about nullclines to try to draw in some solution curves and draw in the hash marks where the vector field's vertical or horizontal. But I think it would be good to just try to continue using Mathematica here a little bit more to, for example, linearize. We can use the Jacobian matrix and plug in the equilibrium points. Remember, you only plug in equilibrium points into the Jacobian. In the Mathematica notebooks, I show you one way you can enter the Jacobian nicely so it'll calculate it for you at an arbitrary equilibrium point, is doing this kind of thing. I'm going to use the basic Math Assistant palette to enter a matrix. In the typesetting, there's a matrix button. And what is the Jacobian? You want the first row to be partial derivatives of the first component with respect to x and then with respect to y. And the second row to be partial derivatives of the second component, g, with respect to x and with respect to y. I can use the basic Math Assistant again and press this button down over here to get my derivative symbol on there. Coming back over here, tells me, okay, I want to differentiate with respect to a certain variable, x for the first one, and then I'm going to do it for the function f. That'll differentiate it with respect to x, but ultimately I'm going to want to plug in the point x0, y0. Replace all is what you want to use to do that, the slash dot. And then inside curly braces, put x arrow x0, comma y arrow minus greater than sign y0. What that'll do is differentiate the f with respect to x first, and then replace the x and y values after that differentiation is done with the particular numbers x0 and y0. And let's try to save some time by copying and pasting to the other spots here. And making appropriate changes. I better make this smaller so you can see it better. Overall, probably have to zoom in there. With this upper right one, I need to differentiate with respect to y, so I change the x to the y. Now go to the lower left, I want to change the f to a g. And in the lower right, change the f to a g and the x to a y. Differentiate with respect to y. So now I've got my Jacobian entered, and now I can plug in equilibrium points. For example, I can plug in the equilibrium point at 0, 50. It's going to be a matrix. I can see what matrix it is by using matrix form. But I think to save some time, I'll just jump right to Eigensystem. To find the eigenvalues and eigenvectors, corresponding eigenvectors for that matrix. Wow. Look at that. Negative 5,000 is one eigenvalue. Positive 110. The eigenvector corresponding to negative 5,000 is 0, 1, which would point straight upward. Any vector parallel to that, including pointing straight downward, would be an eigenvector for that. And the eigenvector for the other one, the positive eigenvalue, is 1, 0, which points horizontally. See if that makes sense. Remember, the red nullcline is the x nullcline, where the vector field is vertical. In fact, it is like your typical species model, where if you start on the y-axis, you're going to stay on the y-axis. And the negative 5,000 was an eigenvalue corresponding to a vertical eigenvector. So you're going to have arrows going toward the equilibrium point right there. It'll be at least a sink in that direction. I'm not sure if it'll be a sink overall in the whole two-dimensional plane, but in that direction, if you focus just in one dimension, in the y variable, it would be a sink. In fact, I know it won't be a sink overall. It'll be a saddle point since the other eigenvalue is positive. The eigenvectors for that are horizontal. And this is a point that I didn't really make in the first 4 videos here about nonlinear systems. But the eigenvector for the linearized system is horizontal. That means for the nonlinear system, the, well, if you will, the separatrix that would come out of that and go away with arrows pointing away will be almost horizontal, at least when you're close to the point. But then it could curve away and be nonlinear after that point. In fact, it's truly nonlinear all the time, but it would be well approximated by a horizontal line near the equilibrium point up there. All right, let's do eigensystem for the other ones. J of 0, 0, so the origin, that's a source. Yep, 2 positive eigenvalues, 2,500 and 160. Eigenvector, it's horizontal, and actually that one's vertical and this one's horizontal. We also had, what was it, 40, 0. Better double check that. 40, x is 40, y is 0, yep. That's the equilibrium point. You only want to do Jacobians at equilibrium points. It doesn't make much sense to do them in any other place. It's going to be a saddle point, positive eigenvalue, and a negative one. The negative one has a horizontal eigenvector. The positive one has an almost vertical one. Negative 253 would be almost vertical, but slightly tilted so that it would have a slight, well, it actually would have a large negative slope, slightly tilted from the vertical. And the other one, we'll stop with that. That's in the first quadrant. X is 30, y is 40. Eigensystem J3040. Yikes. Irrational numbers. So let's get a numerical approximation. We've got two negative eigenvalues. Zoom in on that, about negative 3,223 and negative 96.8 or so. It's going to be a sinc. The eigenvectors, well, this one, you look at it, it's almost vertical. And that one is the most slanted one that we've had so far. It would be one that's close to a slant that would have a slope of close to -1. So I'll try to memorize this information here and go back and try to draw phase plane as quickly as I can to try to make this video as short as possible. One interesting thing that I'm thinking about as I start to draw this is realizing that, yeah, the y nullcline should contain a circle in it, and it did if you remember looking at that, a circle of radius 50 by making this part equal to 0. It also includes the x-axis for y is 0. Let's put let's see, I have the x nullcline in red. That was the y-axis. And also a line about like this. Actually, it would intersect the y-axis somewhere up there, but I don't really care. It's not going to be an equilibrium point up there because it's red intersecting red. Vector field is vertical along here, so a bunch of little vertical hash marks. Maybe I should have stretched this out more. Yeah, I think I better do that quick. So our picture is not too scrunched. In fact, let me just go ahead and make that one that's slanted like that. The y-axis here. Then the y nullcline I had in blue. That was a circle of radius 50. And also the x-axis. Circle of radius 50 was about in here somewhere. It's not a perfect drawing, okay? I'm not going to take the time to try to make it perfect. But I'm making the equilibrium points here. Let me make them in black. The origin, 0, 0. This was what, 40, 0. 30, 40. Not real accurate picture here, but for the sake of time, we'll go with it. And 0, 50 up there. Now let's draw in some solutions. Remember, this was a sink in the vertical direction, but a source in the horizontal. It was really ultimately a saddle point. So the local picture near that point will look like this. Local picture near the origin is its source, like that. Local picture near this point, it's a saddle point like this, and the vector field was slight tilt from the vertical here, in the vertical direction right near this point. And here, let's see if I can remember. Get a better look. We had two negative eigenvalues. The bigger negative eigenvalue, further away from 0, had an eigenvector that was almost vertical, basically vertical. And the smaller eigenvalue, negative eigenvalue, that was closer to 0 is a better way to phrase that, had eigenvector kind of slanted like that. Let's see, x nullcline again was red, so we want vertical lines going through that. Y nullcline blue, we want horizontal lines going through that. Thinking about directions, northwest, northeast, etc., in these various spots. Got to do a little thinking here. Certainly when x and y are large enough in either direction, both the x dt and dy dt are negative if you look at the equations, if you wrote those down. So we're going to have southwest travel up here. And certainly if they're both small and positive, like down here, you're going to have northeast travel for the solution curves as time increases. Down there. Let's see, if we're in here, you can probably guess what's going to happen. We're going to have to go, solution curves are going to come up from here and across. We're going to have to go northwest. The x dt is going to become negative once we cross this x nullcline, and we're in this region over here. Dy dt would stay positive. And up here, I bet dy dt is negative and dx dt is positive. We get something that looks like that. Try to combine all this information, all right? I'm going to do this fast. Listen real carefully. I think I'll start up here thinking about this separatrix up here. Really, it's part of what's called the unstable manifold at this point here. It's got to be going southeast, ever so slightly at first, but then it's going to get more and more southeast and ultimately head toward the sink there. Solutions that start up here are going to head down and also head toward that sink. See this black coming out okay? Looking good? Okay. Solutions starting up here, if they're far enough up here, they're going to head down this way, cross this red nullcline vertically, come down toward the sink. Solutions that have initial conditions up here are going to be going northeast first and then cross the blue curve horizontally before they head down toward the sink. In backwards time, as t goes to minus infinity, these are going to go ahead toward the origin. Solutions in here, like this one, let's go back down to this unstable manifold at this point here. It's got to go northwest, so it's got to keep heading off this way, and it's forced to go up toward the sink up there. Solutions that come close to this point over here would be going northwest for a bit, northeast, excuse me, then cross vertically, then come northwest. Head up this direction, and they do not wiggle like I just drew it there. Okay, that was an accident. I'm trying to draw while I look at the screen. Maybe I should draw while I look at the overhead projector. Solutions over here will be going southwest for a while before they cross the blue curve. Then they'll be heading northwest, head up toward the sink. So other solutions doing the same kind of thing. Some might conceivably get close. At least if they cross the blue curve real close to the x-axis, could get close to the equilibrium point at 40, 0 before they really start heading up toward the sink. You're hopefully getting the idea that this sink is a pretty important feature, that all the solution curves that have initial conditions that start in the first quadrant proper, not along the axes, are going to ultimately go toward this equilibrium point as t goes to plus infinity. X will approach 30 and y will approach 40. A couple more subtleties involved. If I come back to the origin, let's see if I can remember. The eigenvalue, they're both positive eigenvalues, but the bigger one went with the vertical eigenvector, I believe. So that means the smaller one is horizontal eigenvectors, so your curves are going to end up being tangent to the x-axis when they approach through negative values of t as t goes to negative infinity. So, the ones that make it over here and cross the red curve really end up being real close to the x-axis for a long while before they would start heading up there. You might wonder, how would a solution ever do this kind of thing? You can follow my pen up there. How would it ever go up there? Well, it would have to be real close to the y-axis for a long time. Actually, it wouldn't be a very long time. These things actually travel pretty quickly. And believe it or not, even though it's really, really close to the y-axis, ultimately, or when you get close to the x-axis, it would still be tangent to the x-axis if you followed that back in backward time and letting t go to minus infinity. So you really can get solutions that are up there and do still end up being tangent to the x-axis down here, but it's kind of a subtle thing. And we're really more after the overall picture of what's going on here. And that is a pretty good idea of what's going on. In this overall model, if we're ignoring negative values of x and y, you've got 4 equilibria. Origin's a source, these two on the axes are saddles, and this one's a sink. And this is a pretty good picture of what's going on. And if this were an interacting species model, I guess things are pretty happy. I mean, you've got species dying off if they're too populous to begin with, but at least neither species is completely dying off. They are approaching equilibrium. So that's the end of this video.